Now let us move towards quantum mechanical model. So as I told you in Bohr model that he had considered electron as a particle, and thereafter photoelectric effect also said us that waves also made up of particles called as photons. So from this we will reach to a conclusion. There are particles, they both behave like particle as well as wave. It is very much nicely explained by de Broglie. So for a moving particle, we know, let us say if I am considering photon, then the energy of that is equal to mc square, where m stands for the mass of that particle and c is the speed of that. I am applying for electromagnetic radiation. And for wave nature, we also know for a wave, electromagnetic wave, energy is equal to h into nu, or hc upon lambda if I substitute nu as c upon lambda. So this equation of energy for a moving particle having mass m and c speed, and c is the speed of light, both are same in this case. So if I connect both of them, particle nature as well as wave nature, then what happens? mc square equal to hc upon lambda, m into c equal to h upon lambda, lambda is equal to h upon m into c. So we got an expression where lambda equal to h upon m into c. So which indicates that mass is the actually property of a particle, because waves do not have mass. That of lambda, that means wavelength, is the property of a wave. So here how they are connected, forget about these constants h and c. If you look at mass and the wavelength, as mass decreases, that particular object will now behave like a wave because its wavelength will increase. Something moving in a straight line and something moving in a wave manner, what is difference there is the mass or the size of the particle. If the size of the particle becomes so less, now its movement will appear like a wave. If the size is big enough to look at that, then its movement will appear like some particle is moving. So definitely speed will matter there, how fast it is moving, but largely it depends on size of the material. If the mass is very less, now its behavior, moving behavior, looks like a wave. If size is big enough or significant enough, then what happens? You cannot see any wave nature. For example, our movement won't appear like a wave, but a movement of very tiny thing, like let us say if I'm throwing some ant, then its movement may be appearing like a wave for some extent, I'm saying, because even that ant size is also big enough to look at, we can look at that. So if you go beyond that, like if you go beyond like proton, electron, their movement won't be appearing like a particle, because they are anyway moving with the almost speed of light, and at the same time size is so less that their movement cannot be followed or movement cannot be observed. So they will be appearing like a wave. Here this equation can be applied for any particular material which is moving, but this equation must be modified, that because this c is 3 into 10 raised to 8 meter per second, and that is only for electromagnetic radiation. I will modify this equation as lambda equal to h upon m into v, stands for same. This is c also velocity and this is also velocity. Here this is velocity of any object whose value is changing or whose value is not known, not fixed, like 3 into 10 raised to 8 meter per second. Velocity of an object. For example, if I am throwing a ball having some mass, and I am not throwing that ball with the speed of light, I am throwing that with some other velocity. So to signify that, I'll use v as a value here instead of c, because c's value will become a constant and v's value won't be constant. So that will change as per the situation. Mass into v, mass into velocity is momentum. So I can say lambda equal to h upon p, because momentum, linear momentum, is equal to mass into velocity. Similarly, I can also say that kinetic energy is equal to half mv square. So 2 kinetic energy is equal to mv square. 2 kinetic energy divided by m equal to v square. Square root of 2 kinetic energy divided by m equal to v. If I substitute that, then lambda equal to h upon m into square root of 2 kinetic energy divided by m. So this will be lambda equal to h upon 2m kinetic energy, square root of 2m kinetic energy. So this equation can also be used. Remember, this is for electromagnetic radiation, this is for any object, moving object having some velocity. And here if there is a relation between kinetic energy and lambda, you can use this. Even we have kinetic energy can be replaced with stopping potential, like charge into velocity, charge into voltage. Remember this is voltage. Just now in photoelectric effect we have seen that kinetic energy, maximum kinetic energy is equal to charge into voltage. So that can be replaced there. So these are the different formulas that we have to remember, first, second, and this is third and fourth formula. So based on what is asked in the problem, sometimes they may ask the kinetic energy and they will give you the lambda. You have to know this formula to direct substitute that. So here mass, if I am talking about electron, then mass of electron will be 9.1 into 10 raised to minus 31 kg, that you have to remember. Here substitution must be in SI unit. Lambda has to be in meter, mass has to be in kg, velocity has to be in meter per second. H we already know it is a constant value, that is 6.6 into 10 raised to minus 34 joule second. Here voltage has to be in volt, charge has to be in coulombs. So these different formulas we can use, wavelength, and which is largely indicating dual nature. I mean, as mass decreases, wavelength will increase, or vice versa. So both wave as well as particle nature can be explained based on this. If I am talking about, let us say, there, if I take an example of that cricket, where we know that they show overlay of 6 balls after an over. So they show the overlay like this. There are 6 balls, okay, falling on the pitch like this. So what is that? That is the wave nature of a ball. So how ball started and it got hit here and it went like this. Even there is a bat here, you can predict how that ball might have gone if bat wasn't there. So that is the only way to get LBW. That if bat is not present, then whether it will hit the wicket or not can be understood. So here ball is not a particle, not a wave. It is a particle, but still we can understand its wave nature. So how fast it is moving and how fast it has thrown. Based on that we can calculate